Hello, I am Pradeep, and this is a brief overview of our work presented at ICML 2026. Let me begin with the simple thought experiment. Let's imagine an intelligent agent moving in a structured environment. It learns the effect of, let's say, moving east, then moving north, and combining these actions. So in a perfectly flat world, the order should not matter. Moving east and then north should be equivalent to moving north and then east. But many real directed systems do not behave like this. There may be drift, circulation, rotational bias, or some hidden internal state. The agent may return to the same visible location after completing a loop, but um, something might have changed. So its orientation may have shifted, a phase may have accumulated, or its future dynamics may now be very different. So the agent, although it has returned to the same point, but not to the same predictive situation. This path-dependent residue is what we refer to as holonomy, and it creates a fundamental problem for representation learning. The classical grid cell and Fourier-based theories, they assume that actions commute and can be represented using one common set of scalar eigenfunctions. Holonomy breaks precisely this assumption. So the central question of our work is therefore, can an agent still learn a reusable predictive representation when the effect of an action depends not only on where it moves, but also on the path by which it gets there? Our answer is yes, but ordinary Fourier modes are no longer sufficient. They must be replaced by what we call holonomy grid codes, which we are going to introduce, where scalar frequencies acquire a small internal matrix structure. So let me begin with the basic motivation. A useful agent should not relearn the effect of an action at every state. If it understands what moving north does in one part of a structured environment, it should reuse that knowledge elsewhere. That's what humans do. Mathematically, this basically means we want a representation in which one set of features supports prediction under many different actions and their compositions. The classical answer comes from successor representations and spectral basis. The successor representation is the discounted resolvent of a transition operator. So it compresses long horizon prediction into a linear operator. In flat translation invariant spaces, every action is a convolution operator. So Fourier characters then provide one shared eigenbasis, and the different actions only change the scalar eigenvalues. So our work asks what happens when this flat story is no longer valid. In directed environments, actions may have drift, circulation, rotational bias, other topological loop effects. So then going east and then north may not be equivalent to going north and then east, even if the final spatial location is the same. The leftover path-dependent effect is what we call holonomy. We formalize this using projective translations. Instead of requiring translations to compose exactly, we allow them to compose up to a phase written as UG product UH equals sigma GH times UG plus H. Each directed action is then a mixture of these twisted translations. The gauge invariant quantity is a phase accumulated around a loop, And this loop phase is the obstruction to ordinary Fourier diagonalization, which we discussed earlier. So the main positive result is that holonomy does not destroy spectral reuse. It changes its form. We replace the ordinary Fourier transform by a twisted Fourier transform built from irreducible projective representations. Under this transform, every holonomy-aware action operator becomes block diagonal. In the flat case, the blocks are one-dimensional scalars. With holonomy, each frequency carries a small internal matrix. So this immediately gives a compact formula for the successor representation. Under a translation homogeneous policy, the policy transition operator remains inside the twisted translation algebra. Um, so therefore, the successor operator decomposes into independent block problems. Instead of solving one large system over all the states, we transform the signal, invert small matrices block by block, and transform it back. The corresponding basis functions are what we call holonomy grid codes. They are matrix coefficients of projective irreducible representations. Intuitively, they behave like grid codes locally because the underlying space is still periodic, but globally they are twisted by the holonomy class. In the constant flux example, if the loop phase has denominator q, then each block must have dimension q. The transfer story is also governed by holonomy. If two environments have the same holonomy class, their action operators are related by a gauge transformation. So their successor representations and the block spectra transfer exactly. If the holonomy classes differ, exact scalar basis reuse is um, impossible. In fact, non-zero curvature forces internal representational dimension with a lower bound determined by the flux denominator q. So the take-home message is very simple. Classical grid and Fourier prediction assumes flat commuting action geometry. Directed cycles break this assumption through holonomy, and our primary contribution is to show that the correct replacement is twisted harmonic analysis. Basically, the scalar eigenvalues become matrix value spectra, and the ordinary grid codes become holonomy grid codes. This gives a theoretical foundation for generalization under directed actions. Thank you very much for your attention.